Hello everyone. In this video we're going to look at ways to solve triangles that do not have right angles, so oblique triangles, how we can go about figuring out missing measurements in those triangles, and one of the ways that we can do that is the sine law. So remembering that in right triangles we were labeling vertices or corners with capital letters and the sides opposite to each corner with the corresponding lowercase letter, we're going to do the same in oblique triangles. So I have side A on the opposite side of the triangle from angle A. Side B is opposite to angle B, and side C is opposite to angle C. Within this triangle, then, we do have some relationships that still exist even though it's not a right triangle. For example, the measure of all three angles does still have to add up to 180, and that's a piece of information we can use. We do know that the smallest angle has to be opposite to the smallest side, so that looks to be angle A. So I would expect angle side A to be the smallest side as well. And the longest side should be opposite to the biggest angle, which in this case has to be angle B because that is an obtuse angle. You can only have one obtuse angle in a triangle, and the obtuse angle will always be opposite to the longest side. So we have angle B being the biggest. I would expect side B, therefore, to be the biggest. We don't have a nice handy Pythagorean relationship, although when we learn the cosine law, we'll see that there is something kind of similar. But what I'm going to do is I'm going to develop a formula by saying, well, what if I do make a perpendicular triangle here? So I'm going to call that H if I drop an altitude here. Now, what I know is I've now formed two right triangles. And in the right triangle on the left, I know that the sine of A is equal to H over C. Or put another way, H equals C times the sine of A. I also know that in the triangle on the right, the sine of C, because that's a right triangle, equals the opposite, which is H, over the hypotenuse, which is A. Or, put another way, H equals A sine C. Now, since H is the same H in both of these triangles, what that means is that C sine A has to be equal to A sine C because they're both equal to H. And we can rearrange this a little bit. So what I'm going to do is I'm going to divide both sides by AC, because what that does is cancels out the C on the left-hand side, cancels out the A on the right-hand side, and what we're left with is that sine A over A equals sine C over C. Now, there was nothing special about these particular angles. I could have drawn my H on any of the sides. I drew H on side B, dropping down to side B, but I could have drawn a perpendicular dropping down to any sides. So in fact, in any triangle, and this is true in right triangles as well, although we tend not to need it in right triangles, in any triangle, sine of A over A equals sine of B over B equals sine of C over C. So in other words, the ratio of the sine of an angle to the side length opposite to that angle is constant for all three angles and sides in the triangle. This is the sine law. So if I know, let's say two sides in an angle, or I know two angles and a side where one of them is a pair of opposites, then I can use this law to figure out missing measurements. Because I can simply just flip everything over, I could also write this as side A over the sine of angle A equals side B over the sine of angle B equals side C over the sine of angle C. That's an alternate way of expressing this sine law. And in fact, typically I will use whichever form has the unknown in the numerator, because it is a little easier to think about solving this if my unknown, the thing I'm looking for, is in the numerator of a fraction. So let's look at a specific example of what this could mean. So here I have a triangle ABC where I know the measures of angles A and C. Because I know the angles, so I know the measures of two angles, I can fairly easily find the measure of the third angle, because I know that all three angles have to add up to 180. So if I just take 180 minus the 22 minus the 36, I can find that angle B has to equal 122 degrees. So now I actually know all three angles, but I'm still missing a couple of the sides. I'm missing side B and I'm missing side C. But I can find both of them using the sine law because I know angle A and I know the length of the side opposite to A. So that gives me a proportion that I can set up. To find side B, so I'm going to start with the thing I don't know. Side B is going to be in a ratio with the sine of angle B, which is 122 degrees. And this has to be equal to the length of side A divided by the sine of angle A, which is 22 degrees. So since I put a side length in the numerator for my B value, I have to put the side length in the numerator. So now to figure out B, I just do 3 divided by the sine of 22, and then I multiply that by the sine of 122. And what we get is that B is approximately, and I'll use 3 significant digits, 6.79 feet. So that's roughly the length of B. So far, so good in terms of logic, because that is considerably larger than side A, and I do know that side B has to be bigger than side A. When I find side C, I'm expecting it to be somewhere between the two of them. So I can use a very similar equation here. The length of side C divided by the sine of angle C, which is 36 degrees, is also going to be equal to the length of side A, which is 3 feet, divided by the sine of angle A, which is 22 degrees. And again, to solve, just 3 divided by the sine of 22, and then multiply that by the sine of 36. And we have that side C is about 4.71, again, when I use 3 significant digits, feet. So there's my other missing measure. So now I know all of the measurements on this triangle, and it does sort of fit. The longest side is opposite the biggest angle, the smallest side is opposite the smallest angle, the one in the middle is in the middle. And so that is how I could use the sine law to find side lengths. If I'm using the sine law to find angle measures, it's a little trickier. Sometimes there is something called an ambiguous case where we actually don't have information that describes a unique triangle where we maybe get 2 possible answers. For this course, we're not going to worry about that. I will always give you triangles where there is only one possible answer. But it comes of the fact that there can actually be 2 angles with the same sine, which we talked about a little bit with angles in standard position. But as long as I have a situation where, for example, here I already know I have an obtuse angle, it's not possible to have more than one triangle here. So I am missing side C, I'm missing angle A, and I'm missing angle C. Since I don't know side C or angle C, I can't find either of them just yet. But I can find angle A. So because I'm looking for angle A, I'm going to put the sine of A in the numerator of a fraction and divide that by the side length opposite it, which is 58. Now, because I put the sine of the angle in the numerator, I'm going to put the sine of 115 in the numerator here. And that gets divided by the length of side B, which is 95. So in this case, I'm going to take the sine of 115 divided by 95 and then times 58, which is equal to 0.553 roughly. Remember, that is not the angle, that is the sine of the angle. So the sine of the angle is approximately 0.553. So in order to find the angle, I have to use the arc sine. That's the calculator button that has the sine -1 on it. So I take A is approximately sine -1 of 0.553. I'm not going to type 0.553 in my calculator. I'm going to use the answer feature, but I take the arc sine of this answer, and that gives me that angle A has to be approximately 33.6 degrees when I round to 3 significant digits. So 33.6 degrees. Now that I know that, I can find angle C, because C is equal to 180 minus 115 minus the 33.6 that I just found. And again, I'm not typing a rounded value into my calculator. I'm going to use the answer key because I would rather not round until the very end. So I'm going to try and use an unrounded value for C in order to calculate the length of side C. But here what I get is C is about 31.4 degrees. That is the smallest angle. So what I'm expecting to find is that side C will be the smallest side. Now I can use the sine law to find that side like I did in the previous example. So C over the sine of 31.4 degrees. Again, when I use this number in my calculator, I'm going to use a stored unrounded value, not type 31.4. And that is equal to, I'll go back to B. So that was 95, now goes in the numerator because I have side lengths in the numerator, over the sine of 115. So into my calculator, 95 divided by the sine of 115 times the sine of the angle I found, so the 31.4, gives me that C is approximately 54.6, and this was in millimeters. This is logical because I was expecting this to be the smallest side because that was the smallest angle. So that is the missing measures, where A is about 33.6 degrees, C is 31.4 degrees, and side C is 54.6 millimeters.